Your valve springs and push rods could be costing you power and reliability, and you wouldn't even know it. Find out why this time on Engine Masters. This episode could answer questions that you didn't even know that you had. Here's the situation. In a pushrod engine, can pushrods and valve springs affect power even in a situation where you don't have a valve float problem? That's what we're gonna find out. Here's the thing. Let's just look at the valve springs. You know, if you put a really heavy, beefy race-type valve spring in an engine, perhaps you've put a breaker bar in the front, you've turned it over, and you're like, man, this takes a lot of power to rotate this engine. Does that mean that it kills power if you're running the engine with a stiffer spring? It must, because it takes, more work to turn it over. Second thing, you know that when you're setting up your valve train, you might have a pushrod in there and a spring, and you're measuring lift. You know that valve spring flexes right there on the engine stand while you're testing it. But does that happen while the engine is running? And if so, how much power does it lose and what can you do about it? Those are the things we're gonna explore here, all with the help of the guys from Comp Cams. Let me start out by digging a little deeper into the tech of how this all works. Now, the valve spring is what we're really gonna be focusing on here in terms of how much pressure that puts in the system. Now, the other thing we're gonna be looking at is flex in the push rod right here. Note that I've intentionally done my artwork here so that the push rod is not directly in line with the lifter. You can see it's off like this to an angle a bit because that's how it is in a lot of engines, including this big block Ford. And the thing is, when that lifter is moving up and the rocker arm's over here and it's pushing at an angle, that rod can bend. And when it does, it's gonna reduce the lift at the valve because it's gonna take up that motion in here. The other thing that it can do is affect valve duration because as that thing bends, it's not imparting lift at the valve. Therefore, the lift at the valve is happening later and closing sooner, potentially, and we're gonna look at that in this also. Now that we've got all that covered, let's talk about valve springs and sort of how they're measured and how the pressures on them can be determined if they're light or if they're heavy. Let's imagine that this right here was the surface on the cylinder head where that valve spring is seated, right there. And then, I guess I'll draw a valve so that you get the picture of what I'm talking about. And then our spring is here. And then you've got a retainer up here, the thing that has like the little keepers in it and locks and things like that. So what we call installed height is the distance from right here, where the bottom of the spring is, to just to the underside of that retainer. That distance right there is installed height. And the thing is, when you get a spring straight out of the box, it can be really tall like this one right here. But when you install it, it's already been compressed a little bit, even when the valve isn't open. And typically you would see this at like, 200 to 100 on a big block. The big block Ford is unusual. It actually has an installed height of 1.880 inches. So we know that's our installed height, and we can measure with a special tool what the pressure is on the spring at that installed height. The initial set of springs that we're going to run has 210 pounds. Now that's often called valve spring seat pressure. The thing is, it's not pressure, it's actually load. You'll get engineering strokes that'll tell you that's not pressure because pressure includes a unit of area, like pounds per square inch. It's actually load, and it is. It's 210 pounds, not PSI. Now the next thing that we're going to look at is, let's say we've got that same spring, but this time, this valve is open down here like this. So therefore, the spring has been compressed. And once again, right here, you've got the underside of the retainer, and right here, you've got where it's sitting on the cylinder head. You can see that it's been squished. Now, let's just say that it's been squished so much that the valve is at its peak lift, or what we call on the nose. That would be the maximum load that that spring is going to see, is when the valve is all the way open. In the case of the first set of springs we're gonna test on this thing, it has 550 pounds. Now let's talk about what we're going to go to. Here's real world examples of the parts that we're going to be using. This is the spring that's in the engine right now, and it runs perfectly. It doesn't float the valves or anything, and we're gonna install this. You can see that this spring is much taller. We're gonna have to squish it in here into that installed height of 1,880. And when we do, I can tell you that that seat load is no longer 210 pounds. It is 350. And when we've got the valve all the way open, the load is now 800 pounds. That is an increase of 45%. Now that's pressure that we don't actually need for this engine to operate properly, but it does answer the question, does adding that much spring pressure and that much drama in rolling the engine around actually affect power? That's what we're gonna get into. But that's not the only thing that we're gonna test. We're also going to look at that pushrod flex that I described, how this thing can become a spring and get all bendy. And to do that, we're gonna run 2 different pushrods with each of our different springs. I've got one pushrod that is an 80 thousandths of an inch wall thickness. See, the pushrod's basically a tube. It's hollow, you can see through it. And so the metal is 80 thousandths of an inch thick. The stiffer pushrod that I've got is 135 thousandths, so this should have greater resistance to bending. It's also way heavier, but does that matter? These are all the things that we're gonna find out. This is gonna actually be super interesting. It's not something that you see tested very much, if at all. Steve Brule thought of this, and I think it's genius, and I can't wait to learn. We're gonna learn with this engine right here. This is a 514 cubic inch big block Ford. The key that you need to know here is that it does have a solid roller camshaft. Everything that we're testing here really should be reserved for solid rollers as far as the heavy spring pressures, because if you have a flat tappet cam, running way too much pressure like this can wipe out that surface from the lifter to the camshaft. And if you've got a hydraulic camshaft, too much pressure might cause issues with the little plunger and piston and valve that are inside the lifter. So this is solid roller territory, as we love on Engine Masters. All right, I'm gonna go talk to the Steves, and then we'll fire this thing up and find answers to all these crazy questions. All right, this is gonna be an interesting test that came straight from the mind of Brule.
Ooh, that sounds interesting already.
Yeah, the whole valve spring thing. So our initial test with our 514 Ford is going to be with our light spring, which is 210 pounds on the seat and 550 open. And we've also got the thinner wall pushrods in it, right?
85 wall.
So it is 85 wall, which would be 0.085 inches wall thickness on the pushrods.
Baseline is Steve-O.
Well, that's the other question. Will we see the thinner pushrod start to flex and lose power with the heavy spring?
2 or 3 or 4 questions that can be answered.
It's gonna be great.
Yeah.
One test at a time.
All right, fire it up, Steve.
All right.
We just made our very first test in the hunt to find out if heavy valve springs actually kill power, and also if flimsy pushrods kill power. Right now, we've got the lightest of the 2 valve springs that we're gonna run and the flimsiest of the 2 pushrods, and here are our power numbers. 659.9 pound-feet of torque at 4,500 RPM, and the horsepower is 648.9 up at 6,000 RPM. There's not much left to talk about. That's just is what it is.
It is what it is, and it's good.
So the next thing we're gonna do is run into the dyno cell and rip it apart and put in stiffer pushrods. Right now they're 085 wall, and we're gonna put in 135. Ready?
I think it'll surprise you.
I hope so. look at our stiff pushrod torque number, 660 pound-feet, and the horsepower, 652.6. I sort of desperately hope that the stiff pushrods actually made a difference.
Me too.
Look at the overlay. Stiff pushrods are in black, and flimsy ones are in red.
So it did.
Wow, it really made a difference up here.
You know, when I was looking at some of the data before I walked in, it looks to be about 5 up in that area. I mean, I was a little doubtful initially.
Yeah?
With this amount of spring, if that would be that big of a difference. And I think the real proof in the pudding will be is when we put that 800-pound spring on it.
Sure.
Because if that thinner push rod or weaker push rod is flexing and deflecting and losing lift,
Or
it's going to
breaking.
become more exaggerated with that bigger spring.
Wow, this actually makes me happy.
I know,
It's
me
better
too.
Because I
everywhere.
didn't know if we were actually going to see anything.
No, it's better everywhere.
So I'm really anticipating these results being more radical when we go to the really stiff spring and the flimsy pushrod, which is what we're about to do. Or should I say it's what Troy's about to do, because this is going to be a lot. Here's our power with the 800-pound heavy springs and the super spaghetti pushrods. 658.5 pound-feet of torque and 643.7 horsepower, which seems lower
Seems
than
lower.
it was before.
Only because it is low.
Oh,
Show me it.
Let's see.
Have a whole bunch of spring on it.
Oh, look at this. The red lines are the prior test that had the lighter springs and the heavier push rods. The black lines are what we just did with the beefy springs and the flimsy push rods. The thing you can't explain is this.
No, it's...
What if the heavy spring is somehow
Controlling better?
controlling better down here and the push rod's not in distress yet?
Yeah.
And then the push rod starts to go away right here.
Oh.
And then makes more power up there.
What if the pushrod's deflecting and not giving as much lift, raising low end torque?
And duration if it is flexing.
Yeah.
That's a good one. That's way better than mine.
I am getting
That's
smarter
way
after all.
better than mine. You're right. Think of that. That was genius. What Dulcich is saying is that the pushrod's bending, therefore reducing duration in the camshaft, and we know that reducing camshaft duration makes more low-end torque, and that's what's happening. That's genius, Dulcich. I love that when we come up with
Thanks,
excuses that sound plausible.
No, you know, there's actually some merit to that. You know, the proof is going to be when we put the stiff push rod back in it, it should tilt the curve back the other way.
If that's in fact the problem.
Yeah.
But yeah, we lost a lot of power going this way. And to be clear, the reason we believe that we're losing power is because that push rod is flexing, giving up lift,
Deflecting.
giving up duration, and just making a mess of the
Or
whole thing.
is it because the spring is heavier and it's harder to turn?
Well, let's put in the heavier pushrod.
Okay, yeah, we're not going to know really what we're knowing until we throw in the 135 wall push rods, and even then we might not know, but we can come up with excuses because it's what we do. No?
No. Well,
Facts coming up on Engine Masters. Here we go. We just set this up for the final answer about whether valve spring tension has the potential to kill power. We've got our heavy-duty springs in this thing. We've also got our beefy push rods. I'm going to make Steve fire it up on the dyno, and we're going to have a look at the power. Here's our power, and actually, it looks like we're going to conclude the stuff that we wanted to see. The torque with the heavy spring and the heavy push rod is 659, and don't forget the 0.9 pound-feet of torque, and the horsepower is 651.6. Let's look at the overlay of this, and it's got to be compared to the lighter spring with the stiffer push rod, which is the best power curve we've seen so far.
heavy push rod.
Uh-oh. They're exactly the same. There's a little bit of a something up there, but for all intents and purposes, the light spring and the heavy push rod and the heavy spring and the heavy push rod make the same power, the conclusion being that at least in this test, adding 45% more valve spring pressure over the nose does not affect the power curve.
I agree.
My whole interest switched gears as soon as I saw what the better Pushrod did, even with the other spring. It was like, okay, I wanted to go into this looking at valve springs. And you said, well, let's throw some Pushrods in there too, and let's do that. The guys at Comp loved that idea, doing both. And like I say, halfway through, I just went, oh my God, this isn't about the valve spring at all. This is about the Pushrod.
Well, but still, clearly, the whole thing about, you know, the engine turns over harder with a wrench when it's got heavier springs on it doesn't translate into any kind of a loss.
No, it does not.
Yeah. But the Pushrod, you know what we have to see? Let's look at a comparison of either one of these tests with the heavy spring with the light Pushrod. Yeah, look at that. This is a comparison in red of the stiff spring and the light Pushrod, and black is the stiff spring with the good Pushrod. And look at that, massive difference.
Yeah, I would have never caught that, honestly, between us guys. That whole thing about the Pushrod deflection causing the camshaft to actually be smaller.
Appear smaller.
And change something at the bottom, I wasn't prepared for that at all.
Yeah, I didn't see that coming either.
It's so repeatable, I'm very confident, and that's what's going on.
Yeah, and the reason Steve's saying that this is repeatable down here where the flimsier Pushrod makes more torque is because we saw it with both sets of springs, and it goes back to Dulcich's observation that the flexing Pushrod reduces duration.
It does tell me that the other spring is adequate.
Oh, yeah.
The 550-pound spring is adequate for this camshaft because we made the same power, same torque. It was identical. It was the Pushrod that was really significant in helping it pick up.
Let's talk about that in particular. We didn't need to add the stiffer valve spring to this, and there are, in fact, downsides to that, because you might be sitting there going, I might as well stack the biggest spring that I can get on my solid roller camshaft. There's no downside. There is. You're going to wear out parts more. It's still going to flex the Pushrod, and it's still going to have rocker arm difficulties, like it's more strain on the rocker arm could break.
Yeah.
And the axle on the roller lifter.
I was just going to say the lifters. It's a higher strain on the lifter. So
and the seats. You can pound out the seats if you have a lot of closing load.
The valve seats. So while there are downsides to having too stiff of a spring, the question is there a downside to having too stiff of a Pushrod?
I'm not seeing that here.
No, not here. But I think a lot of people have the question, well, the stiffer one is way heavier than the thin wall one. But does it matter over on that side of the rocker arm?
I think it's insignificant over on that side. I mean, that's kind of what we saw. This Pushrod is certainly heavier than the 85 wall or the 80 wall.
And I think that's all the notes that I've got. So our final conclusions are run the lightest spring you can that still controls your cam, but if you go too much on the spring, it's not gonna have an effect on power, and there's no downside to running the stiffest Pushrod you can. And we can also conclude that you really wanna have stiff rocker arms and rocker arm studs, or above and beyond that, shaft rockers.
Right. I like the shaft rockers. They're so much faster to adjust.
Yeah, there's a lot of betterness about shaft rockers.
Yeah, certainly is.
Yeah, what's a good test for shaft rockers? Could we actually get something with like 1,100 pounds over the nose and run it on a rocker stud versus a shaft rocker?
You know, when we talk about deflection, this has got a regular stud in it. If this had shaft rockers on it, would it pick up even a little more?
I'm not sure if we'd see that on this engine, but I think we could do it with something more hardcore.
Yeah, certainly.
And more hardcore is what I love. Anytime I can pull it off on Engine Masters. The thing you can't explain is this.
No, it's...
Oh, yeah, I can explain it if you want me to. Of course. Because the spring takes more power to turn the engine?
But the heavy spring's making more power right here.
I thought you said I was getting smarter.
Can you not snack in the middle of the tape?
Are you chewing?
Oh, God.
He just shoved that beef stick right there on his throat, too.
You want a basic low-risk nitrous plate for an extra 200 horsepower? Well, we're gonna show you the difference between a spray bar plate and perimeter discharge. love nitrous oxide. You touch a button, you get tons and tons of horsepower. I've done it forever with carburetors and plate systems, and man, it's great. But I've always wondered, what is the difference between a carburetor nitrous injection plate that has the spray bars on it and one that is perimeter injection? It sprays it all around the edges. So that's what we're gonna find out here. Before I get into that, let me just touch you up on how nitrous works. In a carbureted application, what we're gonna do is bolt a plate underneath the carburetor, and it's either got that perimeter discharge or the tubes in it, the spray bars, and what it's gonna do is inject extra gasoline into the engine. Now, to burn that extra gasoline, we're also gonna add nitrous oxide. Nitrous is stored in your container bottle as a liquid. It discharges through that orifice and becomes a gas. Nitrous goes into the combustion chamber and it releases oxygen. Oxygen allows you to burn that extra fuel. Burning that extra fuel gives you more horsepower. The other way it gives you more power is by chilling that intake charge like crazy. Here's how we do it. That plate is fed by a couple of nitrous solenoids. They're an electric on-off switch. So you've got nitrous oxide going in the nitrous oxide solenoid, and on the other side, you've got fuel between 5 and 6 PSI going into the fuel side. And that's as simple as it is. All you do to install it is bolt that plate in there, throw some wiring on it, chuck a bottle in the trunk, and boom. You probably also need a nitrous bottle heater. And what we're doing here is a 200 horsepower shot. All of that stuff I told you about, extra fuel and cooling and everything, you just touch a button, you get 200 horsepower. That's adjustable based on jets that you can put on each end of the plate. Now, the thing that gets different here is how we are introducing the fuel and the nitrous into the engine. First, there's the good old spray bar system. This one happens to be from NOS. The way it works is it has a top bar, which is just a tube here with holes drilled in it, and that one is carrying the nitrous. Then you've got the bottom bar, and that one is carrying the gasoline. Now, the way it works is that the fuel is injected at this angle, and then the nitrous is injected on top of the fuel at this angle. So the fuel squirts out at 5 or 6, 7 PSI, low pressure, and the nitrous is at about 900 PSI. So it intersects those two so that it disperses the fuel into the nitrous oxide into the intake manifold. And in this particular spray bar plate, there are holes just for each cylinder. There's 8 fuel and 8 nitrous. You can buy other designs that have a whole lot different thing, like a big shot plate has a bunch more spray holes in it and things like that. So that's one tactic to get the fuel into your engine and the nitrous oxide. This is the one that I've used forever. It's all I've ever used, to be honest. Then there's this style right here, which is a perimeter discharge. Now, it also has that shear of the fuel like I was describing on the 2 different holes on the spray bar, but the holes are all around the edge of the plate. It's actually 2 pieces here, and when the nitrous comes in, it travels in a channel all the way around, as does the fuel, and it sprays out of holes all the way around the edge. This is something that was popularized by Zex nitrous oxide, and I've used them in the old days when they first came out, just sort of for testing. I've never done an A/B test between the 2 plates. And what we're gonna do here is not really look for which one makes more power. I'm curious which one is more tunable and how it reacts to this particular intake manifold. Now, the interesting thing is that Zex and NOS supply different jets for different horsepower levels, meaning a jet that goes into a nitrous plate is sort of like a carburetor jet. It has a metered orifice drilled in the thing, and you might see a 73 and a 64 jet as the tune-up for the Zex plate. That would be bigger on the nitrous and smaller on the fuel. The NOS tune-ups on the newer stuff are staggered like that, but on the older plates like this one, they would recommend like a 74 and a 74, the same size on both one, and we know that that runs a little bit rich. It's a little bit of an antiquated tuning setup. What I wanted to do here is run both plates with exactly the same jetting so that we could compare them equally. And so what Steve Brule did is modified the Zex plate to use NOS jets, which by the way, I would always do because they're more common, they're easier to come by at a typical speed shop. The Zex jets and the Holley jets are different. And those jets that we're going to be using, at least initially, are going to be a number 73 on the nitrous side and 65 on the fuel with about 6.5 PSI of fuel pressure. So that's what we're gonna do. And as we spray the nitrous in each setup, we're gonna be looking, of course, at power, but also the tune-up. We're gonna look at air-fuel ratio globally and also cylinder to cylinder to see which plate might have the air and fuel distributed, and nitrous, better in the intake manifold. It's gonna be interesting. Here's the engine that we're going to test it on. This is my own 408 cubic inch LS stroker setup. Obviously, it's a General Motors LS series engine. The bottom end started life as a 6-liter iron block. It's been stroked out to 408 cubic inches. It's all forged bottom end. It's got large ring end gaps for nitrous oxide. That's something that you should really, really do if you're building an engine and you know you're gonna spray it. Even at a 200 horsepower increase with the nitrous, you don't want the ends of the piston rings to butt from heat. It just causes all kinds of problems. So this is set up for that. It's also very much a tame street drivable engine. The compression ratio is only 9.3 to 1. That's really low. And the reason is I'd initially built it for boost, but the thing is that also makes it just that extra level of safe on nitrous oxide. So about 2 points less compression than I would actually build it for if I was just gonna run the thing around without nitrous or without boost. The camshaft is also very, very small. It's a hydraulic roller, of course. The duration on the intake side is 225 at 50 thousandths tappet lift. The cylinder heads on this thing are 259cc inlet runner. They're from Blueprint Engines. And we're gonna run a carburetor up top this time. It is on a General Motors single plane intake manifold. And I point out single plane mostly to tell you that common knowledge would say if you're gonna run plate underneath a carburetor with nitrous oxide, you want a single plane. In truth, we've tried it on dual planes in past episodes of Engine Masters and actually improved cylinder to cylinder distribution on the dual plane. But the results that we're gonna see here with these two plates might be different if you were dealing with a dual plane. In fact, they might be different on different single planes, but it's still gonna give us some information on what could happen. Now, of course, I'm running it with a carburetor, and it is a Holley XP 750 CFM. Because the LS engine doesn't have a distributor, we're gonna control that with an MSD box to pull timing out when we're on nitrous. So there you go. I'm gonna sit down with the Steves, and we're gonna run my glorious little LS motor on a 200 shot of nitrous oxide with 2 different plates. Here's the thing. This LS makes 540 horsepower. What's your rule? 30%?
30, 35, that's a safe number.
30% is 162 horsepower gain. His rule is that it is safe to use nitrous oxide up to a 30% gain on the engine's base horsepower, 35.
Yeah, like on a 500 horse deal like that, or something, I'd go up to 175. I wouldn't really want to go anything past that.
Yeah.
So I think the jets we chose are kind of in that area.
We're gonna run 72 nitrous jet on both of these things.
Okay.
Yeah. I think it'll be pretty good. We're gonna fire it up now and run the thing without the nitrous and just get ourselves a baseline, and then we'll start to rip on the gas.
Yeah.
Go?
Go.
Go.
Thank you.
Bye.
You know, it's interesting to look at our power curve here because we've run this engine a bunch, including yesterday for a different episode, and it made 500 pound-feet and 545 horsepower. And now our power numbers are 516 pound-feet of torque, and it's making 560 horsepower. The only differences are we added 2 nitrous plates, so that's a 1-inch stack, right?
Yeah, that's basically a 1-inch stack because we've got a plate that is 1 inch. This is a 1/2-inch thick nitrous plate, so we put a 1/2-inch phenolic on top of it. It's just so everything was the same for all the plates.
So it's just like running a open carb spacer, and it made that much difference. Anyway, pretty good baseline power. What are we gonna do first? We're running the NOS, just regular bar plate.
Single old bar.
Yep. And you've got the 72 jet on the nitrous side. Yes. And what's on the fuel side for a jet?
We've learned from experience that it takes a smaller fuel jet than nitrous jet. So what we have in it now is a 7264 is where we're gonna start. I think that'll give us a pretty good close call. We can adjust fuel pressure, maybe even a thou jet from around there, but we want to just make it where the tune-up's good and we can just run it from plate to plate.
Yeah. You're gonna learn something, Dulcich.
Oh, yeah.
We've gone through all our safety checks before we run nitrous. We've set the flowing fuel pressure, we've made sure that the solenoids work, we've made sure that the ignition timing is retarding, we've opened the bottle with the engine running just to make sure that the nitrous isn't leaking through the engine, through the solenoid. Everything is perfect. The first one that we're going to run is the NOS conventional plate, just with 2 spray bars in it. After that, we'll get to the perimeter plate and then doing some stuff with the crosshair. But right now, standard cruising model NOS plate with a 72 nitrous jet. We'll see the power and we'll see our tune-up. I know the first thing that you want to know is the power that we just made with nitrous oxide. It is 774.2 horsepower. I'm good with 775 on that. And the torque is 724. The thing is, those numbers really depend sort of on where you hit the button, especially the torque. It's going to change pretty radically if you stab it, at 4,000 or if you stab it at 5,000. The thing is, we're not just looking for horsepower in this episode because, come on, we know that nitrous oxide makes horsepower, and if you don't like your number, you just put in a bigger jet. That's it. What we're looking at is the tune-up. So where do you want to start sort of analyzing that?
Well, I know that we could put more timing in it to make more power. There's a few things we could do, but where we started specifically for a reason was to start to look at cylinder-to-cylinder stuff. And so I think that's probably what we should look at next.
I agree.
Yeah. This is a chart of all the different cylinders. The thing is, if you look in the mid-range, let's pick 5,500 RPM, we have number 8 cylinders at 16.7 to 1 air-fuel ratio. That is scary, scary lean. Really, we would like to see this thing at 12.0. Does that make you happy?
I'm not nearly as concerned about that 17 to 1 number as you are because it's momentary. And nitrous is under so much more pressure than gasoline, you are always going to have a 2 to 3/10 of a second long spike in air-fuel ratio. So it's not a matter of what the number is, it's how long it's there.
Okay, you're right, there's 17 here when you hit the button, but then 16, 16, 16, 15.6, 15.8, that still scares me.
This is obviously an issue. But when you look over here and you see something that's 15 and now it's dropped to 13,
right,
or something that's 14 and dropped to 12, those numbers are acceptable.
I think what we're thinking is that when you have a spike lean, it's because the nitrous oxide gets to the cylinder far faster than the gasoline does.
Yes.
The gasoline's at 6.5 PSI.
Right.
The nitrous is at 900 PSI.
Yeah, so. Exactly.
But it's still got lean holes. I mean, even down here at 6,000 RPM, I mean, 15 to 1 scares me. The rest are like 12. With a plate system, you can't pick one hole to fix.
No, and that's what really bothers me about this. So what we're probably going to end up having to do is give up some power in one or more cylinders to try and correct that number 8 so it doesn't burn up.
It seems to me that our only choices here to fix that 1 or maybe 2 lean cylinders are try and put a big carburetor jet in the right rear to see if we can get more fuel to number 8. I haven't had a lot of success with that, but we could try it. Or globally change the fuel and the whole thing, make it all richer just to save that 1 cylinder, yeah?
Yeah, I mean, those are both solid approaches to try. But the first thing I'd like to do is go take a look at a spark plug. Sensors do go bad. Bosch sensors, NTK sensors, they do fail at some point, and particularly with leaded fuel. So what I want to do is go take a look at the spark plug. That's the first thing that sees combustion, and we're going to be able to tell whether it's really as rich or lean as we suspect that it is.
On that same line of thinking, would it be a good idea to swap the sensor on 2 different cylinders and run it again and have a look?
Absolutely.
Okay, so those are what we're gonna do to make sure we don't blow up my LS motor. All right, let's have a look at Mr. Sparkplug. We pulled out this number 8 spark plug to see if it had anything going on, and it looks flawless. If it had spatters of aluminum on it that would have come off the piston, that would be really bad. Instead, we're looking deep on that porcelain, and there is like what, a 32nd or 16th of an inch tall black ring around the bottom of it, which is perfect. The other thing is you can read the timing requirement or the timing like performance a little bit by looking at where it burns on the ground strap. And if you don't have enough timing, it'll be over here by the tip. If you have too much timing, it'll fold all the way over here to the edge. You want it right there at that bend, and that's where we're at. Anyway, this is all good. What we did, since we found nothing here, is we took 2 of our oxygen sensors and swapped them cylinder to cylinder so that we can go look at another pull and find out if maybe it was the sensor that was giving us that really lean reading on number 8. The number 8 cylinder is still reading lean on our sensor, and so we don't think the sensor's bad because we swapped them cylinder to cylinder, and so we're gonna do something we've never done before. One way to attempt to richen one cylinder in an engine is to change just that jet in the carburetor that's nearby. It's not that effective on a manifold like this. What we're gonna do is go enlarge this hole in the spray bar that's pointing towards that number 8 cylinder and see if we can put more gasoline into that cylinder. Here's our final pull with this thing after we were messing around so hard trying to get that number 8 cylinder rich. He drilled that oversized hole in the spray bar, and honestly, it did nothing. But let's start with the horsepower, and then we'll explain that. This made 772 horsepower and 737 pound-feet of torque. The problem is this tune. We still didn't get that hole any richer.
No, it's, you know, past experience, it's hard to tune a single 4-barrel manifold with an issue in one hole. It's hard to get things diverted to just a single cylinder.
Yeah.
With a tunnel ram, you can poke around right over every cylinder, but with a single 4-barrel, it's tough.
Let's pull up that graph so we can have a look at exactly what happened. This is a little confusing. This is air-fuel ratio in each individual cylinder. Red is before we started all our like extreme tune-up tactics, and black is after. You can see we really couldn't affect the shape of what any one cylinder was doing with this thing.
No, and the spike we're seeing here, that's when the nitrous is activated. We've talked about that, where it goes leaner momentarily for 2 or 3/10 of a second. Then it settles back in. That's also the horsepower spike. It'll make more power there, but not for a long period of time when it's that lean. But this cylinder here, we just, you know, we got maybe a 1/10 or 2 change out of it, but really almost nothing.
Didn't. So, and we know that it's not the sensor. It could be the box that's reading it. We'll maybe find that out when we put the next unit on. By the way, we know it's not this carburetor doing this because we've run this thing on 187,000 dyno pulls. So it's not that. I think the bottom line here is that you cannot pick one cylinder off with a plate, and we just need to move on. All right, we're going to give up on solving that and move on to the perimeter plate system and see if that fixes anything. Changing the plate. At a baseline power of 560 horsepower, we hit the button and turned that into 789.8 horsepower and 750 pound-feet of torque. So that's really good, but we know that nitrous makes power. The story is in the tune-up. Now, this is a air-fuel ratio curve for every cylinder in the engine. Higher is leaner, lower is richer. This spike right here is when we hit the nitrous button. The nitrous gets into the engine before the fuel. It goes lean. So really what we're looking at is down here. We do have one fairly rich hole at about 11.5 or 11.7 to 1. And the leanest that we get is 13.4 to 1. This is safe and good, and the grouping is tighter than what we had with that other plate. And our tune-up's identical. So we're looking at same jet, same fuel pressure, same ignition timing, same carburetor jetting, and it's just happier with the perimeter plate system. So I guess to conclude, No one's gonna drive around with a plate system at this power level and actually have O2 sensors cylinder to cylinder. And I think the first thing to comment on that is people have used spray bar nitrous plates for millennia. I mean, they've been around for decades.
We used them 40 years ago.
We used them 40 years ago. We use them forever. Everyone's put a zillion laps on them. And in general, you don't kill holes, or if you do, you're looking at spark plugs and you know that that's a risk. So I guess what I'm saying is we saw that one cylinder. The spark plug didn't tell us that it was in any kind of distress. You know, the O2 sensor did, the spark plug didn't.
Right.
40 years ago, you would have looked at that spark plug and gone, I'm golden, and run it, and you would have never had a problem. But we do know now, which is why we end up being happier with the perimeter plate in this application, because I guess the data just makes us feel more warm and fuzzy.
And that's really some tough power to outrun anywhere. You put that on the street, who's gonna run with you?
Yeah, it's pretty good. Man, I love nitrous. We need to test more with nitrous. Oh, you know what we have? I want to do a fogger so that we can individually tune each cylinder.
Yes.
You know what? That's a promise. We will do that on a future episode of Engine Masters. It's another Engine Masters intake manifold showdown. This time, it is single plane versus single plane and dual plane versus dual plane on a 514 big block Ford. It's another episode for you big block Ford lovers who nag me all the time going, we need more 385 series big blocks on Engine Masters. And here it is. I wanted to do an intake manifold shootout, and I'll tell you this time, it was limited by what was available on the market in the days that we were setting this thing up. I was able to get these 4 intake manifolds, and I'll tell you all about them in detail. And once I knew what I was able to get, I had to fit them into the type of engine that would reasonably be used with these intakes, and it actually ends up perfect because it's right in the middle of the road. See, the bulk of the market, the right down the middle of the road guy, is gonna be a street strip unit that could use any one of these intakes, either the high-rise dual plane or the mid-level single plane. Are you gonna wanna build your thing that runs 6,500 RPM or less and use it in a big old heavy truck, or are you gonna use it in a drag car? Well, either way, you're gonna have answers out of this episode. You see, the engine that we're going to use is a Ford Motorsport 514 cubic inch crate motor. It's nearly stock. It makes in the neighborhood of 640 to 50 horsepower and 630 to 40 pound-feet of torque, depending on the configuration. It's only 9.8 to 1 compression ratio. In some episodes, you'll see Dulcich and I sort of, I don't know, not ridiculing the thing, but wanting more, wanting our big block Ford to make 750 horsepower, but instead, this is a pump gas, tame, drive it anywhere kind of engine, but it does have a solid roller camshaft, but it doesn't RPM above about 6,000. So it is the perfect player for what we're doing here. Let me tell you specifically what we've got. First of all, on the dual plane side of things, the ones that are gonna favor the lower RPM, the more truck-oriented manifolds, are going to be the Edelbrock Performer RPM. This is a high-rise dual plane. I'm gonna say that this is significantly better for this application than an Edelbrock Performer, which is a much lower-rise dual plane. The thing is, we also have the Edelbrock RPM air gap intake. The key difference visually, of course, is that this is all cast as one unit, whereas you can pass your hands underneath the intake runners on the air gap. They advertise these as being able to flow cool air under the runners to make more power and potentially have less vapor lock. So that's the story on the dual planes. Then over here on the single planes, interestingly, we have an airflow research intake. Now that is designed specifically specifically for the Airflow Research bullet cylinder head. And as such, it has sort of a rectangular port, which is differing from the rest of these, which are oval or nearly round. Let me talk to you about what we're using for a cylinder head and how that relates to these intakes. The cylinder heads that we're using on this crate engine were called a Ford Super Cobra Jet. They were designed by John Kazi way back in the day, maybe 20 years ago. And these heads have altered valve angles and things that have improved flow, but they also have a much larger port window than you would see in a regular passenger car cylinder head. I can show you that by showing you this. This gasket right here is for a regular 429 or 460 up to about 1987 in a car or truck. This is a Super Cobra Jet intake gasket. Now, if I overlay them here and line them up perfectly, you can see on this side that there is a big difference in the size of the ports. And you can see how it's not only the size, but it's the location as well. And so that's what we're dealing with, are cylinder heads that are this size and 3 intake manifolds that are closer to this size. The important part being that the head is bigger than the intake manifold, and so in no case do we end up having a problem with a step offset in the wrong direction. While the head might be capable of more than some of these intakes are, we're still gonna be able to demonstrate the capabilities of these. So there's our story. We're gonna run all 4 intake manifolds. First, the 2 dual planes. Is it true that the air gap is actually different than the Performer RPM for the big block Ford? I don't know. Can an AFR rectangle port intake make power on a Super Cobra Jet head? I don't know. Can the manifold that was originally delivered with the Ford Motorsport crate engine actually top all of them? I think kinda probably. Let's go. How much do you guys love intake manifold shootouts?
I love them because they're brainless.
Okay.
Brainless? What do you mean brainless?
Well, other than you two looking at them, I mean, I just get to bolt them on, push the handle, and say, here's the numbers.
Power.
Oh, yeah, I guess brainless.
I love them because nobody does like head-to-head comparisons of this stuff, or at least I don't see it anymore.
No.
You know, I get emails every day about guys saying I picked this because I watched the episode.
Yeah, we're gonna have good answers, and this time we're gonna do 2 dual planes and also 2 single planes on the Ford. So our first test is going to be the regular Edelbrock RPM.
Performer RPM is actually their designation.
Right, the Performer RPM. I always call them just RPM, but that's
Me
right.
too.
There's a Performer, and then there's the RPM air gap that we'll get to later on in the episode.
So the first victim's the Performer RPM.
Here are power results for the Performer RPM intake manifold. We made 636.6 pound-feet of torque at 4,200 RPM, and at 5,700 RPM, we saw 615.7 horsepower.
Pretty good stuff for a little dual plane.
Is it?
I think so.
We were gonna offer it a milk bone, honestly, when you weren't here.
Yeah.
Yeah, we were gonna take it for a walk. I guess we're sitting here going, if we had 514 Ford with these heads, honestly, this has 9.8 to 1 compression, so it's low.
Yeah.
It's a street motor, it's a pump gas motor, and it needs another 20 degrees of camshaft. But then we wouldn't really be able to do this story with the dual plane intakes. I think that is what it is. Our next step is to find out if, in fact, the RPM air gap is gonna be better, so we gotta go swap it out. All right, the trick on the big block Ford intake installation is to tuck under the distributor and plug it into the water bypass, and then go for the plonk. Straight down. That was pretty good. We just did our intake swap. Now we get to go find out the power of the Edelbrock RPM air gap. And now the results of the RPM air gap intake manifold, 638.6 pound-feet of torque at the same 4,200 RPM. Also the same RPM that we saw with the other manifold up at the horsepower end, 5,700 RPM is 614.8 horsepower. We know nothing until we see the overlay. What? This is unacceptable.
I know you don't like it, but what is the trend that you kind of see there?
I don't like it because it's counter to my preconceived notion. Because I'm telling you, you and I tested the RPM versus the air gap on small block Chevys and saw nothing, which is the danger of drawing a global conclusion over one single test, I will admit. But here's my other thing. Standing here on the counter with both these intake manifolds, the port window at the opening is the same. Measured it with a caliper, measured multiple ones with a caliper. The depth of the plenum on both sides is the same. And visually, there's no difference in the runners at all. But Edelbrock says that the ones in the air gap are bigger, and that would support that.
Yeah, it would kind of tilt that curve just like it's doing.
I mean, to be clear, what we're seeing here is the black lines are gonna be the RPM air gap that we just tested, and the red lines are the performer RPM, the first test. And you can see that the performer RPM is making a bunch more torque at the bottom end, but when Steve said it tilts the curve, you can see exactly that, because it's the air gap that makes more horsepower at the top end,
but only making more horsepower past peak.
That's an interesting point too, which supports the fact that it is really more airflow. But I'm really surprised at that result.
But you know, that's exactly what they said, is it has a larger volume, which, I mean, that's exactly what
But for that to be true, it means that if the plenum's the same and the port mouth is the same, it means that the runner this far between the plenum and the port mouth has to be bigger.
When they say that it's larger, does it give a percentage?
It told me 3.3 square inches total. It doesn't tell me what it is.
You know, in that sort of volume in that area, I don't see that as being a big deal. That could be thousands literally on walls and floor and just kind of, in general.
Square inches is only a point measurement at a certain position along the runner.
Right.
And usually it's minimum cross-sectional area, and we don't have a data to compare with the other intake manifold, but that would indicate, like Steve said, a bigger manifold.
It comes back to what you always say every time we test intake manifolds. What is it? You know what you always say.
Oh, you can't tell a thing until you've run it.
Well, you know what? Every episode we test these, I go, the manifold we always recommend is the Edelbrock RPM. And now I have to question, what's the difference between the RPM and the air gap? Because my knowledge comes from the Chevy mostly. All right, whether I like it or not, the dyno doesn't lie. We have to conclude this time that for low-end power, the Edelbrock RPM is superior to the RPM air gap, but the RPM air gap is going to be better if you have high RPM, bigger camshaft, bigger engine, anything like that.
All of those things.
Fascinating. It's why we do this stuff. And the next thing we're going to do is try the single-plane intake manifolds. The first one up is going to be the airflow research. Next up is going to be our airflow research single-plane intake manifold, and I'll remind you that this is a little bit of an unfair deal because this manifold is designed specifically for the airflow research head. And you can see that the port window on it is more rectangular than anything else that we've got here. And if you look at the head, that is a big oval, and that's a rectangle. So I'll just give you a refresher on how this is going to fit. This is the same gasket that we've got on the cylinder head. It fits the port almost perfectly. If I hold it up here to this manifold, you'll see that the manifold, despite being a rectangle, is not being shrouded by the cylinder head at all. Swoop her in. We're going to test this with the same Holley HP 950 carburetor that we're using on the other intakes. The HP has slotted base plate bolt holes so that you can bolt them onto a manifold designed for a 4150 Holley with a smaller pattern, or you can bolt it to a manifold that's intended for a 4500 series Holley, which is a Dominator. You have to use a Dominator gasket to do that. So here we go, bolting on our 4150 carb onto our Dominator intake manifold. Our power numbers are at higher RPM points than we saw with the dual plane. For example, we're now looking at a torque peak of 4,400 RPM instead of 4,200, and that peak is 639.6 pound-feet of torque. The horsepower has now jumped up to 6,000 RPM, and it's 628 horsepower. We're gonna compare this to dual-plane intake manifolds, which almost naturally are gonna make more bottom end, but maybe not as much top end. So let's first compare it to the RPM air gap. Textbook difference between a single plane and a dual plane intake manifold. The red lines here are the dual plane air gap, making way more low end torque and less top end. The black lines are the AFR bullet single plane, making less torque and more horsepower.
Yeah, do you notice that the crossover on the power is right around peak torque?
Yes, it is, right around peak.
Yeah.
It's 100 RPM lower than peak torque. Let's compare it to the regular Performer RPM, which should actually make more bottom end beef. The blue lines that we just added are the first intake manifold that we tested. It's the Performer RPM. And you can see it's making even more torque down here, much to my surprise, and just a speck less horsepower up top.
It would certainly be application specific between the single plane and a dual plane. But if I'm going to pick a dual plane, I think I'm going with the Performer RPM. I mean, it picks up enough bottom end. I'm not trading off that for the bottom end it gains.
And if you don't buy the air gap, you don't lose tools under the intake manifold.
Or bolts.
We call it the bolt gap.
Yeah.
The bolt gap. Knows you always drop stuff down in there, and it always fills with oil and gas for us.
It's a nice catch.
Yeah. To this point, we think that we're going to argue that the Performer RPM, not the air gap, is our favorite dual plane. And as far as the single plane goes right now, it's dealer's choice, whether you want low end or whether you want to drag race the thing and RPM it. Our final answer is going to be when we install the final Edelbrock manifold, which is the one that finally has the same size port window and same shape as the cylinder heads. Our final player, the Edelbrock Victor 460 with the Super Cobra Jet port on it. There we go. Once again, the 950 HP 4150. Here's the power numbers. We made 638 pound-feet and 638 horsepower. The torque came in at 4,600 RPM, and our horsepower peak is still landing up at 6,000. That's pretty stout peak numbers from what we've seen so far.
It's all to be seen.
We got to compare it to the Airflow Research Bullet single plane.
This may be the one time where visually the intuition was correct.
Really? Black lines, the Super Cobra Jet intake manifold, the Edelbrock unit, and the red lines are the Airflow Research. And it's weird, the Super Cobra Jet, or the Victor 460, made a bunch more power above peak torque, like above 4,500 RPM, and really it's a trade-off. Why is it that they performed about the same down here and not up there?
You know, the bottom end on this particular manifold actually I think is exceptional that it did hold on to the bottom end and still made more top end. You know, visually it's a larger manifold.
The Victor 460, yeah.
So intuition-wise, it's like, okay, it's bigger than the AFR, it's a single plane, maybe it'll make a little more peak. But I'm impressed that it was able to hold on to the bottom end.
So the Victor 460 ended up making more power than the AFR up top, but is it possible that when we're doing a port offset, meaning the intake manifold is much smaller than the cylinder head, is there any kind of turbulence in that offset that actually slows down airflow?
I guess a flow disruption would be a pretty logical explanation for what we're seeing in a dyno curve up top.
I think part of it might be, too, is where the port is located in the intake manifold versus the intake port. Maybe it's actually entering the air in a not very good area of the intake port itself, where a port that's aligned properly would come right off the floor and have the nice turn. It might be that it's coming off of a wall or something because the port alignment as far as position is not very good.
Interesting. So I bring that up basically to say what we're doing here is not as much an intake manifold shootout on the winner as it is an investigation of what's available on the marketplace marketplace and what happens.
Exactly.
And in this case, we think there's a couple of reasons why the AFR is not moving as much air up at the top end as the larger Victor 460.
Well, and in all fairness, we know that that manifold works because we've done the head comparo, and we know that the AFR head and that manifold make better power than the...
Which is a matched team, because
Yes.
the AFR head is designed
Yes.
around that same port shape as the intake
So the head
manifold.
can't make better power if the intake manifold won't support it, so...
Also a solid conclusion. What I would like to see now is, we know that for this combination, the Victor 460 is our favorite single plane, and we know that the Performer RPM is our favorite dual plane. So can we have a look at both? Wow, that's pretty massive, actually. The black lines are the single plane and the red lines are the dual plane. I gotta be honest, there's no way I'm choosing the dual plane on this thing. I can go ahead and give this all up because I'm gonna be making more than 550 pound-feet of torque from the step. So who cares? I want the horsepower.
You know, we talk about this all the time about contouring the engine. There's no special blower cam. It's just that you can give away some bottom end for some top end. And this is kind of the same situation. The engine's big enough that I don't think you need more than 550 pound-feet at the bottom, but you can sure use that at the top.
That's a big difference. You can really see where the airflow starts to lay over on the dual plane. There's no way you disagree with that, right?
No, I mean, you're seeing a textbook example of single plane versus dual plane right here. I mean, it's pretty evenly matched. So if you wanted a lot of low-end torque, for whatever reason, the dual plane's got it.
Yeah, like we talked about earlier, application. You're not gonna pick the single plane for your pickup truck. You're not gonna pick the dual plane for your drag race car.
And that's a clear conclusion for the episode, but there's a couple of other things. We were able to compare two dual planes, two single planes, and dual plane versus single plane. And so our final answer is, I found out that there is a difference between the RPM air gap and the Performer RPM on the Fords. And more RPM, more horsepower, more displacement, you want the air gap. But this benefited with the Performer RPM. That was the light bulb moment for me in the episode.
Yeah, the whole thing is good. I always love these intake manifold tests because we go in presuming we know all of what's going to happen, but we always learn something coming out of it.
For sure.
Yeah.
And I feel more than ever that the things I learned here were not that shootout thing of, oh, this one's the winner. It's more an application thing and some knowledge about what happens with different port shapes and things. So, pretty cool.
Yeah, I liked it.
I really want to build a larger displacement, bigger power Ford big block.
Ford, that could, you know, 600-inch Fords are not out of the question at all.
Super easy in a stock block.
Some of the stuff I've seen with the Fords, some of the builders say, oh, this thing was way easier than building a Chevy.
Really?
So, yeah, I mean, it was surprising to me, but it's a possibility.
We'll call that guy because we need to test that junk on a future episode of Engine Masters. But I can't live with myself till we do one more thing.
Let me guess.
Dominator! Last test, we're gonna find out if we can make a few extra horsepower with a Dominator carburetor. Now we're super happy. We just made 649.5 pound-feet of torque and 650.5 horsepower. Let's just say at 600 horsepower, you should probably be looking at a Dominator.
That's why they call it the Dominator,
Isn't
right?
that the greatest name ever conceived
yeah.
for a speed part? I love it. Horsepower makes heat. This time on Engine Masters, we're gonna show you how to love that power by keeping your cool. I don't think there's anybody who knows more about torturing themselves with horsepower than I do. I mean, I could give myself a header burn from like 100 yards away. You should see some of the junk I drive. Headers right up against the floorboards, automatic transmissions blasting me with heat. I burn my feet, my toes, my hands on stuff all the time. You know how it is. Making horsepower makes heat. Strangely enough, this episode of Engine Masters is not gonna be about making horsepower at all. Instead, we're gonna talk about how to attenuate that heat problem in your car. First of all, we're gonna look at reflective heat shields. This is the type of stuff that you would put like on the underside of your floorboard or in your engine compartment to try and reflect header heat back at the engine and keep it out of the passenger compartment. So that's gonna be part one. Next, we're gonna have a look at header wraps. Do any of these super special wraps actually keep heat in the header and away from your fingers and inside your car? That will be the last thing that we figure out. What I'm gonna do first is wander into the cell and show you how we have set up my 408 LS engine and a big contraption to test all of these heat shields, which will be compared to a bare sheet of steel. Does any of this stuff actually work? We're gonna find out. Here's how we're gonna test all of these reflective heat shields. Every single one of them is stuck to a sheet of 22 gauge steel. I've got a handful of those. Now we took that sheet of steel and we've clamped it here right next to the header. We had amazing difficulty getting that to get hot, which is kind of stunning. You would think that putting a piece of steel within a 1/4 inch of a header running at wide open throttle would make heat. What we ended up having to do is a bunch of things. First of all, the engine, it's gonna be running at 5,000 RPM under a given load for 30 seconds. We had to go that hardcore to get any heat transfer. And to be honest, in your car, that could end up being worse because there's a number of things in the dyno cell that want to be working on cooling off that piece of metal. The first one was airflow. There's a lot of wind in here. And so there's cooling from convection, which is a fluid, in this case air, passing across a mass or an object and pulling the heat out of it. We had a lot of convection cooling, and so that's why we've got these blocks here that are preventing airflow across the header and across the sheet. The other thing is we wanted to make sure that we didn't have conductive heating of the sheet. Conductive is when the metal is touching the metal, and that's how the heat is being transferred. These materials are not designed for that. They're designed to prevent radiative heat radiation. They reflect heat back. And so we've got a 1/2 to a 1/4 inch gap, depending on where you look at it, between the header and the piece of steel. That way, these things can work the way they're intended to do, which is reflecting heat. Now, the other thing that was curious about all of this is what we had to learn about measuring heat. We ended up with this Fluke thermal imager. This is $24,000. The image from this is what you'll end up seeing with me and the Steves out at the table when we're talking about all of this data. It not only reads the room, but it also has specific points of temperature that we're reading. We're going to be able to read temperature right here on this header tube, and then at 2 points on our sheet that's trying to reflect the heat away. Now, the interesting thing is we learned about emissivity, which is the fact that anything that is at anything above absolute zero emits actually infrared radiation as it's sending its heat off. And that's what this measures. The problem is it can't measure something that's too shiny like a mirror. It's really technical. Bottom line, we were able to solve our technical problem with a can of barbecue spray paint. So all of these are painted black so they're not too reflective so they can actually read. The dyno is not gonna give us any data logging. We're going to be observing what's happening on the screen and letting you know what's gonna happen. Our first test is gonna be heating up a just bare sheet of steel, and then Troy will run in as we go and change from one heat shield to the other to the next, and in the end, we'll sit down, rank them from best to worst, and let you know what happened. Usually at this point in the show, I'd be having a sit-down discussion with Steve Dulcich and Steve Brule, but we decided to rip right into it. Here's what Dulcich and I are gonna be looking at. That is the screen that's showing us what the infrared camera is seeing. We've got temperature points here and here on the plate, and right here you can see it on the header tube. Steve Brule's in there running the dyno test. He's gonna rip this thing up to 5,000 RPM at a load that will be consistent throughout all the testing. And Dulcich, if you could please help me keep an eye on the temperatures so that we can agree on that, and I will be writing those down. We're gonna start with the bare plate, and then Troy is gonna go in and burn his hands and change plates out as fast as we can. Then we'll come back and I'm gonna show you all of those plates and discuss it so that the Steves will see it at the same time that you do. The first heat shield that's gonna be run here is the lava shield. How's that possible?
That doesn't make any sense.
No!
It's a heat-absorbing mat.
Whoa! I have to go inspect this.
That's insane.
Is it touching? It just picked up like 100 degrees. It's 100 degrees hotter than no mat at all. Let's go look at that.
200 degrees almost.
That actually made it worse.
It made it hotter.
Now we've taken that same piece of metal that had the lava shield on it and flipped it over so that the shield is pointed out. It's not facing the header. We'll just see if there's a difference there. It's the same. That's wild. I really can't wait to run the next sheet. This one is Reflect a Cool from DEI. Another DEI product this time, but it's Reflect a Gold. It's the gold one. The next one is the Cool It sheet from Thermotech. Our last test is gonna be the only one with a little bit of insulation. It's the Sticky Shield from Heat Shield Products. All right, welcome to what we call the Engine Master's living room. We usually get to this point a little bit earlier in the show when we're all three sitting and talking. I think it's the first time that we've tested before we brought you in to talk about stuff. And man, did we test. There was a lot of stuff that just went down trying to make sure that we were nailing this test as tight as we possibly could. But we weren't able to actually nail precise degrees on this stuff, but man, were we able to see some trends that are overwhelming and really unrefutable, because we went back and forth and tested over and over and over, rebaselining, making sure that the trends were the same.
You made me do it over
and over. Hey, it's my motor running at 5,000 RPM at full load for 30 seconds over and over and over.
That's something else that we don't normally do the way we test it. I mean, I was parking the thing at 5,000 RPM, wide open, for 30 seconds at a time to make sure we were generating header heat to the point where, you know, headers were stabilizing, what did you say, somewhere around 950 or still creeping up, but kind of taking that
once we started getting in the groove, we were able to really nail a consistency where the surface temperature of the plate and the header has the same at the starting point, and you ran it at 30 seconds, and the thing ended at the same header temperature every time. So that was a lot of repeatability. It seems.
Well, what I saw was a lot of this is kind of like almost like when you're looking at EGTs. The way that you drive the car
makes a big difference.
Makes a big difference in how the ending EGTs are. So what I was doing was I was cruising at 2,500 for approximately 30 seconds until those two temperatures would stabilize. Being the same, you'd give me the sign of go, and then I'd run it for 30 seconds wide open.
Yeah. And so we did that a lot. I mean, we worked really hard, and we feel comfortable with our results, even if you can't nail it down to within 1 degree. You can nail it down within 10 or 20 degrees, either way, I would say. And here's the reason why we went to all that trouble, because this was a shocker. This is a product from Heat Shield Products that's called Lava Shield. It looks cool. It looks kind of like carbon fiber. It's all neato. They say it's got, you know, some, I guess, basalt in it, like lava rock.
I have to say, it lends a very attractive look to the sheet metal.
It does, and it's extremely thin and light. Here's the thing that we absolutely could not believe, and we tested it 4 times, and we tested it with the lava rock facing the header and facing away from it, and every single time, it added surface temperature. To be specific, we saw surface temperatures on our 4 tests of 302, 312, and 291 degrees versus the baseline of 157 to 171. So clearly, this is doing something to retain heat and amplify it rather than shield it. Put the header here and read the temperature here, and it was hotter than a bare piece of steel. And unbelievably, we had the same problem with this product. This is made by DEI, and it's called Reflect a Gold. Once again, super thin material. Very, very thin, and obviously a gold color to it. Best run that we got out of this one was 246 degrees versus 170 at the worst for a bare piece of metal.
Still 70 degrees warmer.
How does it happen?
Heat
I don't
goes
understand.
in, but heat can't come out.
I guess it doesn't make sense to me. But we tested it over and over and over again.
It's like a nice winter blanket.
I can't explain it. Those two products claim to be heat reflective products, and I read the websites over and over and over and over, and they didn't do that. But then we have the DEI product called Reflect-A-Cool. This is the first one of our aluminized silver surface products, and it also has a little bit of thickness to it. And this reduced temperatures by neighborhood of 20 degrees.
It's pretty good.
It pulled down the temperature 20 degrees
That's
or
good.
so that worked. And then we had the product from Thermotech called Cool It. And this one's very similar, but it has some texture to it and probably just a hair more
Looks like a
thickness
little
to
more
it.
material.
And on average, this seemed to knock down about 25 degrees from our baseline surface temperature. So that also worked. And then the product that I looked at right out of the box, and I think you all did, and said, this is gonna be the one that absolutely works. And the reason is that it is an aluminized cover that has some bumps in it, but it has a thin layer of fiberglass insulation to it, and that insulation is gonna be the key. This is from a company called Heat Shield Products, and it's their sticky shield. This knocked 40 degrees.
Well, it's the thickest of the products. Our intuition says this looks like it should be better.
Right.
This isn't that much different than home insulation. When it's thicker, it does a better job.
I think the best insulator is air, always.
There's a lot of air pockets.
It has a lot of air pockets in it. And so really what I wanted to do here was not like a brand-to-brand shootout, but I wanted to get a variety of different styles of reflective products, and not the stuff that is sound deadener that goes on top, but the stuff that I thought you would run on the underside of your floorboards or on your inside your engine compartment under your hood. And I think my conclusion is that the stuff with insulation, with some thickness, with some fiberglass is always gonna be better than just that thin coat. This one is gonna be the one that I would pick. This is, once again, the sticky shield. On average, it would reduce roughly 39 degrees off of our testing.
That's pretty good.
That's a lot.
The other thing that I would say in all of our testing here is that we struggled to get heat into these things. And in the car, I can tell you it's way worse.
Yeah, and part of it is the length of time, I think. The duration that a piece of material is subject to the heat. Like when you've got your feet on that trans tunnel and a header's laying underneath it, and it goes on for 10 minutes, 20 minutes, a half hour, an hour, and pretty soon it's at the point where the whole floorboard is the same temperature as the collector on the header.
And when you were doing the testing, both the surface temperature of these as well as of the header was continuing to climb with time. He had it parked at 1 RPM wide open, and it just kept on going up and up and up. And you're not cruising 5,000 RPM at full load on the highway, but if you're cruising a longer duration, there's less airflow underneath the hood. And I've literally burned my sandaled feet in many, many roadkill project cars.
Yeah.
Next thing I would like to do is the age-old header wrap. I got the top 3 heat shield companies that I could tell from shopping at Summit. The most common stuff is the Thermotech. That's their copper, Generation 2 copper. Then DEI is another big brand. This is their titanium. And finally, the Heat Shield Products Inferno exhaust wrap. So,
it's a good name.
Once again, I got these not as a shootout for these 3 brands, but because these seemed to be 3 different approaches, just sort of the old school kind, the titanium, and the copper. I don't know anything deeper about them than that, other than we're gonna find out if they work or not. I think what I actually would like to do is re-forward data, and then we'll run it again once we've wrapped them.
Okay.
So let's re-aim and get a baseline. We did this test once on Engine Masters where we used header wrap to find out if the wraps make horsepower, because a lot of the wrap companies claim that that's true. We were not able to duplicate that scenario. They say that by wrapping the pipes, it makes it hotter inside the pipe, which makes higher pressure, which makes it escape out the back faster, which you know, pulls, what's the word? It like evacuates the exhaust better and makes horsepower. We were unable to prove that. That's not what we're doing this time. This time we're just trying to look at the surface temperature. All right, rather than clamping it, Steve's gone with the half hitch. I will cut off the excess, and then you've proven your abilities. You can do the other two as well.
I knew that was coming.
Yeah, I know.
But I'm enjoying wrapping headers so much, I'm looking forward to doing the rest of them.
Normally I would get a wider material for wrapping header tubes, but this is what was available, so I got 1 inch on all of them. He's doing about a half overlap on each wrap, like so. Does it seem to you that the titanium wrap is a little bit more flexible, sort of like softer, fabricier?
It just has some very endearing properties. You may be right about that.
Yeah, it seems just softer. It looks cool. It's like semi-metallic.
Yeah, the question is, how's it gonna do as far as the heat handling properties?
I think these are all gonna work. You're doing impressive work, Dolchek.
When it comes to working with fabric, I'm your guy.
We've been through a lot of heat shield products on our LS engine. Now we're doing header wraps. Steve just wrapped 3 different brands on 3 different tubes, and we know that we had 1,000 degrees or 950 to 1,000 degrees in those tubes before, and now Brulee's gonna test it and see what kind of temps we see after the header wraps. All right, he's gonna give it a full 30 seconds at wide open throttle at 180 RPM.
It's cooler.
Yeah, looks to me like it knocks a couple hundred degrees out of it, anywhere from 150 to 200 degrees. This is actually gonna be pretty good. I like these results. The thing is, I'm gonna alert the audience to the fact that you can't really expect any 2 header tubes to be identical in temperature to begin with.
No.
Because of cylinder-to-cylinder distribution and coolant layouts in the cylinder head for a number of reasons. But I can tell you that all of these wraps knocked heat out of the surface temperature, which is good. So our very first one on this cylinder was the Heat Shield products, and it knocked out 168 degrees. And then we had the DEI titanium wrap, and that one knocked out 106 degrees. And finally, the copper one, which, by the way, there's a ton of copper dust in this stuff, it knocked down 162 degrees.
Wow.
Yeah, so if you just look at the raw numbers, we've really killed 160-something degrees out of both of them, and the titanium was only 105.9. I can't say that's really a difference in the product. I mean, it's notable, but it could just be differences in the way that header tube's making heat. I don't know.
I'm impressed that they work that it knocks that much temperature out in general.
Yeah.
And the thing I'm even more impressed with is how well the 2 of you guys can actually wrap header tubes, because I suck at it. I suck at it.
I use hose clamps because I won't deal with those little tiny stainless clamps or anything. He just tied it on there like a mariner. You should have seen him.
Like a mariner, thanks, Freiberger.
I figured you would like that.
Yeah, I did like that a lot.
Yeah, you were the captain. You were the pirate of exhaust wrap.
Yeah. He told you that's what he was going to do.
He said, I'll wrap it up right now, matey. Anyway, I think we learned a lot on this episode. We went through a lot of different heat shielding products, and mind-blowing to me. I still can't fathom it. We tested it over and over and over again to make sure that we were correct. 4 times we had products that raised the surface temperature above what we saw with a bare piece of metal. That was the standout crazy thing to me in the episode.
Yeah.
I did also learn that if I'm gonna deal with a heat shield product, I'm gonna use the one that has a little bit of insulation in it. I think ultimately air is the best insulator.
Yeah, I mean, it is a little more fragile. You have to be more careful putting it in to make sure that it doesn't get torn or something. But if you're careful, and once it's in, it obviously added the best insulation.
Yeah, under carb or something, that is gonna be the best stuff. And then the last thing we did, of course, was the header wraps. I expected them to work. They all did.
Yeah.
And so I'd say performed as expected. You know what, though?
What?
I'm solidly ready to get back to actual data instead of observations and actual horsepower instead of just heat.
I kind of felt left out this episode. I mean, I was blocked. I couldn't see the header. I couldn't even participate because I couldn't see it. Yeah. And I had no numbers to share with you. So it was just...
yeah, you were just sitting there pulling the handle.
Yeah.
No, we'll let you do more next time, I promise, as we make more horsepower, which is what we really prefer to do every single time on Engine Masters.
I'm enjoying wrapping headers so much, I look forward to doing the rest of them.
Just don't sever an artery.
Oh.
There we go.
If I severed an artery, would you get the other two?
We might wrap for the day.
Okay.
You getting fiberglass in your fingers?
No. No, I'm being very cautious not to get fiberglass in my fingers.
Are you getting titanium on your fingers now?
My fingers are already titanium, bro.
This episode of Engine Masters is just simple and fun. It is an air filter element shootout. This time we're gonna find out which color air filter element makes the most power. Not really, but kinda, because man, you can see they come in a variety of colors and styles. There are so many air filter elements available on the market these days. I just want to do a quick shootout to find out if there's really any differences in any of them. So you're gonna get two things. You're going to get paper elements versus cotton elements, oiled elements, and then you're also gonna get a brand to brand shootout. So I bought everything that I could that appeared to be different that was in stock at summitracing.com at the time we did this show, which is June 2023. I brought my crib notes because I wanted to give you what all these are and what the prices are of them, starting from cheapest to most expensive. First, we're gonna test an All-Star Performance paper filter. That one is $12.99. Mr. Gasket paper filter, $15.72. Then Summit has their own line of air filters, and now we get into the cotton gauze oiled air filters. These are available in blue, black, or red. Strangely enough, red is $34.99, and you can get the other colors for $26.99. I don't think there's a difference in performance, it's just the colors. Next up, we have one from Spectre Performance. This is $31.99, available in red or black. I got the black, which I thought was pretty cool. Edelbrock sells one that's called the Pro Flow in blue, black, or red. That's $34.95. Then we get into the green filter. That's actually the name of the company that sells them. It's not just the color. The green filter is $58.42, and then the K&N is $77.99 on sale at the time we're shooting this. They're normally $89.99. Now, as we test these, one thing we cannot do is judge the value of the filtration on any of these. We don't have a way to contaminate them uniformly, and we don't have a way to sort of analyze what particles are being passed through them. So this ain't that. This is going to be a power test, but I can also sort of give you some observations on each one of these. The two paper filters, I really wanted to get a super cheap one that hardly has any pleats on it, and I couldn't find that. And so the All-Star and the Mr. Gasket are extremely similar, though clearly not made by the same company. They're not the same exact thing. The thing I'm talking about on pleats is air filters can often be judged on how many folds they have, you know, per inch or all the way around the thing. If they have very few folds, that means there's much less surface area on the filter, and that's gonna tend to mean that it won't pass as much air and that it won't catch as much dirt and stay cleaner and useful as long as if you have a whole bunch of folds, but I couldn't find a super cheapie. So that's just a little bit of information that applies to both paper filters and the cotton gauze. Other observations that I've got to get into are that the only two here that are made in the United States are the green filter and the K&N filter. Now, I got to lead with K&N because this is the company that actually popularized high-performance cotton gauze air filters. They did it way back in 1969. They really invented this marketplace, at least as far as I know. And that product, while it is the most expensive, I will tell you sort of just based on intuition and handling it and fondling it, it's the highest quality unit here. It fits better, the folds are more consistent, the way the wire is like embedded in, it seems more solid, it's a little bit heavier, so that is the nicest unit. The other one made in the United States is the green filter. Here's the thing about that. I took the green filter, and I took all of these actually, and held them up to the light and looked through them. That green filter, you can see a lot of light through the thing. You can actually see some voids in it. And I'm like, what is going on with that? And I wondered to myself, how can this filter anything compared with these other guys? And I read up on their flyer, and here's the deal. They say that they use less cotton layers in their filter than, for example, the K&N. And they say that their oil magnetically charges the screen so that it can catch negatively charged dust particles. I suppose the cotton is there then to catch the positively charged dust particles. There's no way we have to verify all of that. However, the company's marketing does explain why that one seems to be more see-through than the others. What we're gonna do is throw all of these on one engine and just test them, and essentially we're gonna look at horsepower and find out what the airflow is on them. What engine are we gonna use? My 408 LS. Super simple. All we're really using it for on this episode is to suck air and find out which filter is best. Okay, guys, ready for the least ambitious episode of all time? Yeah, this is gonna be simple and easy, but when I came up with the idea, you're like, dude, people ask the question all the time, so here we are.
No, I like our discussion. You know, I mean, some of the most basic things really are what guys are the most interested in.
No, I want to know too, and I think we learn something every single time, but I do want to add a little bit something other than just air filter elements. I think we should still test it just with an open carburetor. In the past, we've seen that it loses power with a dropped base. I think we should run through that again.
I think we saw that with a drop base with an element. I wonder about just a drop base.
That's true. We could run just a flat base, just a drop base, and then start putting filters on it after that. Yeah. However,
oh boy, money time.
We're not gonna see a difference of more than just a dyno variance of 2 or 3 horsepower with any of the filters, including the paper wood.
Ooh, I'll take you on that.
Yeah?
Yeah.
You will?
Oh, you betcha.
Okay.
No, I'm actually gonna go with you and bump Dulcich another 20.
Okay.
I'm in. There's gonna be more than 1 horsepower difference between them.
That's not what I said.
Dyno variation.
So do we call that 2 or do we call that 3? 3.
3? Get out of here, Brule. 3?
We can't just look at peaks either. We're gonna have to look at the average. We're gonna have to agree that it made no difference.
All right, I'm going all in.
So we have a friendly bet on the table about what's gonna happen with the air filter elements, but first we're gonna fire it up and run it with no air filter on it at all, and then we're gonna probably fiddle around with some bases, and then we'll get into the elements. Steve, let's see our baseline. On the open carburetor, nothing modifying it at all. We saw 508.6 pound-feet of torque and 541.3 horsepower. So let's run out there and we'll test both the flat base and the drop base, and then we'll come talk about what happened.
Perfect.
Our first test with no filter and just a base is with the dropped base. And now the flat base on the carburetor. Steve's about to pull up the test with the dropped base on it so we can compare it to what we saw with nothing. Whoa.
That's a lot.
The comparison here is the black line is with no base on it, and then we put the dropped air filter base, and look at the power it picked up. It made 5 horsepower up top. I bet you the flat base does the exact same thing.
You're talking one.
Yeah, the flat base does the exact same thing. It is 1 horsepower difference. We're not counting that. So legitimately putting some sort of air transition into the carburetor helps.
It helps.
Which we've seen many, many, many times. I just didn't expect 5 horsepower all the way up top.
Well, the reason I thought it was kind of cool to put a base on it is because you see so many guys at the track. If they're drag racing, they'll take the filter off. But I see some guys with no base and some guys with a base, and I think it's important. One is to kind of keep the engine temperature away from the air inlet, and then to contour it as well.
And also the reason why it makes 5 horsepower up there and not down here is simply airflow demand.
At a much higher speed, so that contour makes a bigger difference.
Yeah. When we do our filter testing, which base do you want to use?
I want to use the flat one.
Yeah. We'll test it all with flat, and then I think at the end I want to go in and test with a filter, the flat and the dropped.
I think that's a good idea.
Now we're gonna start testing filters, and we're gonna run in there and test our 2 paper element air filters, and then we'll come back and pick a winner on that, if any.
Our first test is going to be the All-Star Performance 14 by 3-inch paper element. That's the cheapest filter in the test. I'm going to add this paper gasket. You'd be surprised how much dirt can get right between this edge and the carburetor air horn. And all set, ready for testing.
Now the basic paper element from Mr. Gasket. What's on the screen right now is the power with a flat base, but no filter on it at all. So let's see how much power a paper air filter element kills. Black lines is no filter, red lines is with a filter, so that you can see that you do lose some grunt everywhere in the curve by adding that paper filter.
Pretty significant from top to bottom.
How did the Mr. Gasket do? Now we're looking at a comparison of these 2 paper filters. The red lines here are going to be the Mr. Gasket. The black is the All-Star. They're the same. Those 2 paper filters really are identical. I think the worst part of all of this to me is that I couldn't get a Fram filter. That's the one that I always used when I was a kid because I wanted that orange rubber on there.
That orange rubber was
the key.
Yeah.
Yeah. So honestly, I think most of these paper filters that have a pleat count like this are going to do that. The next thing that we're gonna test is all of the oiled cotton gauze air filters. And I think I wanna run those maybe in order of price. Does that sound right? So I think the first one up is gonna be the Summit. We're into our air filter element shootout. We've already seen that our paper filters kill a little bit of power versus no filter at all, but now we're looking at our aftermarket oiled cotton air filters. First one up is going to be the Summit brand oiled cotton gauze air filter element. And the cool black looking filter element is from Spectre. Next up is the Edelbrock ProFlow. Can you guess which filter this is? It's the green one. And our last filter, the biggest name in the aftermarket, K&N. We just came back from testing a whole bunch of oiled cotton gauze air filter elements, 5 to be exact, and we've pulled up the power curves of all of them right here on the screen. And as you can see, they're all pretty much the same, but there are differences. So on a zoom in, that's the difference right there. It's interesting. You can actually see they're fairly well grouped together, except for the green filter, which happens to be the green lines, actually is up ahead, but it's by a really minute amount. So among all of the oiled elements, the difference in peak torque is 1 pound-foot. And then the difference in peak horsepower, 2.8. Then the average, meaning the average from the whole range of RPM, 2.1 on torque and 2 horsepower. So that's, that's the difference that we're looking at.
Amongst these brands,
amongst all of these filters. So while this looks like it's standing out right here, if you look at the scale, at best, it's 2.8 horsepower. So we established that I believe that all of our oiled filters are essentially the same, although the green was just a speck better by a horsepower or 2. So what we're gonna compare here is that green filter that was the best of those to the worst of our paper filters. And I might add that by worst, I mean by 0.6 horsepower. And so that is going to be the All-Star paper filter in the black lines and the green filter in the red lines. So you can see, in fact, the difference between a paper filter and the oiled filter can be significant enough that we need to do this. Although I misspoke at the top of the show, because what I meant to say is all of the oiled filters are the same. And what I said was, all the filters are the same.
Thanks, you just lost 40 of my dollars.
I did. Yeah, I know.
Thank you, guys.
Yeah, you won because the ultimate gap here, remember we said that we would go within 3 horsepower? Well, at peak horsepower, the difference here is 4.4. And at peak torque, it's 2.7. I still would think that we would see it closer here and further apart up there.
Well, and we are as far as, if you look at the power curve, it kind of it does do that.
Well, regardless, I think we know that the paper filter doesn't make as much power as the oiled filters, but I think we also assume that the paper filter filters more.
Yeah, looking at those 2 filters, you cannot see through one of them.
Yeah.
The other one, you can look right through it.
Well, the other consideration on these, though, is how much dirt can they hold before they start to degrade performance? That's one of the claims to fame of, like, I think K&N initiated that entire concept. And the other thing that Steve and I have dealt with before on Roadkill and Roadkill Garage is driving through a massive puddle, driving in the rain with your paper filter.
You get a paper filter wet and it won't let any air through it. As a matter of fact, you'll just suck it right into the can.
The next thing is I really want to try the drop base versus the flat base. Which element do you want to do that with?
The green.
Do we want to, though?
Oh, yeah.
You do?
Yeah, oh, absolutely.
Because it was the best one?
Yes.
I think that's fair.
Okay.
Yeah.
Now we're starting our last test. First up is going to be the green air filter with a flat base, and then we're going to change it over to the dropped base and see what happens. And now the drop base. This time, we really didn't see anything. There's one little glitch on one data point where the drop base actually made a little more power, but all throughout the curve, nothing this time.
I wonder if part of that has to do with the demand, too. I wonder if this might show different results on an 850 horsepower engine where there's a lot more demand and you've restricted that area.
And I'm not sure if we tested it earlier on a carburetor with a choke horn.
Yeah.
Because the choke horn sticking up off the top of the primaries is going to get way closer.
That's a really good point. If we did that, then there's almost no room there. I've measured that. I've seen it. It's like it shuts it down to almost nothing. The drop base is actually always kind of, in my experience, showed to be kind of a nice contour and entry into the top of the carburetor. So.
Well, and while picking at minutia, to be fair, this green filter made the most power. I mean, it made more power than no filter at all. It might be making the airflow a little bit more linear through there.
We're just using that at this point because it doesn't seem to be at all restrictive. It's a spacer between the bottom and the top. So we've still got basically an open bottom that's contoured.
All right, I am prepared with conclusions for this entire episode. The first thing is there's nothing here that we can declare at all about filtration quality on any of this.
No.
Yeah, so just to reiterate that. The other thing is all of the testing you've seen here is going to apply at this power level. It's not going to matter if you've got a 283 running 10,000 RPM making 500 horsepower, or if you've got a 540 that somehow only makes 540 horsepower.
It's about the airflow.
It's going to be about the same.
Not seeing huge differences, I would say that anything from this power level down is fine.
Exactly. Yeah. But if you are dealing, as you said, with 850 horsepower, these things are going to start to be more of an issue. I think what we saw with these filters all being virtually the same, I mean, within 4.5 horsepower, which earned him $100, that there was nowhere to go at all, because when we ran no filter and then added the paper and it only killed 5, well, it's not like the other ones were going to be able to add 20.
No, small gains and losses.
Not necessarily in order. I think we just found out that not in all applications does it matter whether you have a drop base or a flat base. And earlier than today, I would have said, oh yeah, we tested it. Flat bases can kill power.
And it's also going to depend on the top.
The other thing is what we've seen, I'm going to say every time, is that some sort of a base or plate or velocity stack is always better than an open carburetor. It just smooths that transition at the edge.
Yeah.
I think we learned that paper, as far as we have seen, let's say it tends to kill power versus no filter at all. And that the oil filters tend to make more power than the paper filters.
By a little bit.
In this case, it could be bigger in different applications. I think we can also say the two papers that we tested made the same power. I really wanted to find one of those papers with like no pleats in it that had almost no surface area. It might have made the same power, but it would have clogged much faster.
Yes. Yeah.
The oiled filters that we tested, they were really all the same except for this green one, which made another couple horsepower. And maybe there's a reason for that. Looking through it and reading their brochure and watching the power, it's like, okay, I don't know if it filters anything, but it did move more air.
Yeah, that was kind of an interesting explanation on how it actually filters. But it's not because of layers of material. It's some other magic that's going on there with positive and negative ions.
Yeah.
Yeah, okay.
I think that's about it, other than the pros and cons of oil versus dry, which is oiled filters cost a lot more, but
a lot more one time.
You can wash them essentially forever.
Yeah.
If you're a guy willing to do that.
Are you?
No.
Neither am I.
I end up not having time, and one time I did it years ago, I made a mess of it. If I get a car that has an oiled filter in it and it's a caked up mess, as my junk tends to be, I throw it away.
I'm willing to wash them.
Yeah.
And it's not so much even having to re-oil them and spend all that extra time. I'm just willing to wash them. As I'd mentioned earlier to you, I even have a K&N filter in my heating and AC unit because I take it out and I go wash it off and put it back in.
Yeah.
And I bought one filter and now it's been there for, 8 or 10 years.
And you're not throwing away as much junk.
And honestly, I don't want to sound like Mr. Greenpeace, but that's truly,
it is.
I felt bad about throwing away just garbage and, because I was changing that filter once a month. And so now it's one time and I'm done.
Well, that turned into a lot more conversation and thought over something that I thought was going to be just a totally brain-dead test. I hope you picked up something from it because we learn something every single time we do this show that's called Engine Masters. Okay.
Oh, well.
I love guys like this, where you just go, no, we're going to really bet now. We're not just going to wand things around. And all of a sudden, have you ever noticed that same sound in their throat when they start to choke?
I'm good for it, guys. All I have are hundreds in my wallet.
It's okay, I've got change.
Hello, xin chào tất cả các bạn nha. Lại là mình đây. Hãy ra những video hay cho các bạn xem. Các bạn ơi, các bạn thấy hay thì hãy like và comment cho kênh của mình thật hay nhé. Cảm ơn các bạn đã theo dõi kênh của mình. Ok các bạn nha. Chúc các bạn thật nhiều sức khỏe. Đón xem nhiều video hay hơn của mình nha. Chả chị bảo cho nó cho hành với lại cho rau nhé. Rau ấy. Kiểu dưa đấy, rau dưa đấy. Không, mưa bão lên rồi.
Dọn qua xét đi.
Sấm.
Cả xét nữa. À giá xét tao đó. Cái cửa
xét viết ti. Xét đánh xịt điện.
Xịt điện ở đâu?
Ở trên này.
Cái lại có rồi.
Tầm tiếng họ ấy sửa. Tầm tiếng là có điện.
Kinh, mở mắt ra nhìn đã thấy kinh.
Khiếp à?
Đấy là nó rất là hay.
Không vấn đề gì. Hả? Chị ra chỗ nào? Chỗ đây thôi mà. Chỗ gần cổng chợ thôi mà. Có. Thế á? Ừ. Buồn nhỉ?
Đưa lấy luôn bộ áo rồi cho người ra đưa ướp ép một quả
Ăn đồ bún chả. Ăn mì đi. Mì thì vào hãm thôi. Ăn mì cay cũng được. Ăn mì cay cũng được. Mì cay. Đây đây. Mì đỏ lưỡi. Giờ tạnh rồi. Ừ? Có ship vậy. Quên không nhớ được con máy nhỉ. Thế thì đợi nó hơi lâu đấy. Đợi lâu lắm thì hắn tạm nước kia vậy. Qua đây không cái?
Cái này nấu không?
Ừ.
Đây là mì nấu.
Chị ăn qua đây.
Không, chị ăn thôi. Chị ăn con này còn đều. Chắc không cay lắm đâu, nhìn màu.
Chắc con xôi không? Em hết xôi rồi, còn hơn 20 chiếc bánh mì thôi.
Mì khô đéo ăn.
Bánh mì nướng. Thôi, dạ ship về đây nguội mẹ mất. Ship về lên đây nguội bố mất rồi còn đâu nữa. Chị cắm nước đi. Cắm nước. Ui giời, cái gói này ăn thì hỏng lưỡi.
Biết đã cay tốt. Cái gói đấy hơn, cái gói da cầm cay lắm. Gói này đỡ.
Gói zin này đỡ.
Đây cho nó xong đấy.
Chị có ăn mì cay không?
Hả?
Không ăn mì cay à?
Không, ăn được gì?
Dạ. Không là gì đấy. Em nghĩ là ngon. Gói này là nó ngon. Gói này đỡ cay đấy nhỉ. Ăn được. Không có gì. Chị cắm ít nước à?
Cái mì này phải nấu.
Mì
Không
này
chín được.
mì này mì nấu.
Không chín được.
Nó ghi chữ mì nấu thôi.
Còn mình vẫn hai bà vẫn bán.
Hai bà đấy phải bán rồi. Bà đấy là bà chị, còn bà kia bị ung thư nghỉ rồi.
Đấy, ấm.
Ui giời, nhiều nước thế.
Thế vừa.
Nước. Nước vào đây. Đây một bát thôi. Úi giời. Thử bát tô. 2 bát tô nước.
Nhiều quá nó nhạt lắm.
Đấy, được rồi. Hôm nay nó. Hello cả bà con nhé. Bà nãy em bảo rồi, hôm thấy nói chuyện bà bảo bị ung thư mà.
Ừ, bà bảo chị.
Bà không bảo chị bà bị ung thư gì.
Ừ.
Thì bà nghỉ mà.
Bà bị từ ngày xưa rồi.
Thế à?
Bà lâu rồi nhưng mà mỗi lần phải đi xã ấy.
Xã chị à?
Ừ.
À, thế bảo đội kia bắt đầu nó mới nói chuyện.
Đội nào?
Đội cờ động đầu cầu đấy. Thế là bảo sao bà? Thế bà
Ở nhà chuyện gì cũng biết.
đâu đi ra mua bánh mì, mẹ năng bờ bu thì chị biết rồi. Tổng hợp của các câu chuyện ở đấy.
Không có chuyện gì khác khỏi bà.
Ừ. Mình mua bánh mì thì bà ấy bảo là cái bà bánh mì bên kia thì em hỏi bảo ô thế bà bên kia hôm nay mấy bà ấy nghỉ mà. Thế em mới hỏi bảo bánh mì bên kia không cạnh tranh với bà nữa hả? Thế bà bảo là bị ung thư nghỉ rồi thôi. Thế chuyển sang cho chị gái bán rồi. Chuyển sang cho chị gái. Nhà 7 người. Ừ. Khiếp cái gì? Các cụ ngày xưa buồng trứng nó đông. Các cụ ngày xưa nó ấy mắn. Thôi ngay nhỉ.
Buồn. Cứ lần nào chị đi cũng bị.
Chị lấy đũa chưa? Lấy cho em cái. Hôm đi mua xôi xéo thì hết. Hôm nay thì đi mua xôi này thì đóng cửa. Quá nhỏ. Ôi trời ơi, không ăn à?
Không.
Ăn em hãm rồi gói đũa này.
Không tao ăn.
Ui. Cho quất vào nó thơm. Làm nhỏ đã. Tí cay thì không cay ta cho thêm.
Cái người thiệt với mình ngon, không nghe gì cả.
Cái ăn không bảo gì.
Không.
Nay có đi học không?
Không, nghỉ rồi.
Lại không học nữa.
Khóc.
Không.
Khóc quá.
Không tải được nữa. Em bảo rồi, Bé quá chưa đi được đâu. Bọn trẻ này để cho nó lớn lớn một tí, nó quay qua riêng cơ thì nó còn đỡ, quay người quen. Mời mọi người ăn mì cùng mình nhá. Xin chào và hẹn gặp lại các bạn nhé.